So interesting, you can see those spring coils that they got in there. Counterbalanced, a little weights and all the rest of it. So it's a pretty simple circuit, and it looks like it's on a ceramic PCB, hybrid module type PCB. There's the inputs, power. Okay, so I've pulled the meter off. You can see where I've marked where the red and black wires were. So I've reverse engineered the circuitry on here, and after a bit of internet searching, it appears to be an SAK215, which is not what's printed on the chip. This one's actually printed, manufactured by Texas Instruments by the looks of that logo, and has the part number MIC2/C. So it marries up very well to the SAK215, which, as it turns out, is a custom designed device for revolution counters. So it's a pulse shaper circuit for revolution counters. So the data sheet is in English, but there's a lot of suggestions it's probably like a Japanese component. I don't know who the brand is. I should know, but of the original SAK215. I'm not sure who it is now. But yeah, this one's actually manufactured by Texas Instruments. It makes me wonder whether there's a license and all that sort of stuff you can get, because I can't find what the internals of this particular circuitry is. It's not a 555 timer, that's for sure. But effectively what it's got is between, you've got 3 power pins. So pin 1 is your ground, and you've got pin 8 and pin 7. And it's unusual. Pin 8, this says VB supply, but the sample circuitry tells you to feed it with a 82 ohm resistor. And more than that is of pin 7, you've got your positive supply being fed through a 100 ohm resistor as well. So it turns out between pin 7 and ground, pin 7 and pin 1, it's effectively a Zener diode, or at least the circuitry equivalent to a Zener diode. And the data sheet actually lists that that pin 7 is called voltage supply in parentheses stabilized, with a symbol of V7, so the 7 is obviously pin 7. And it has a min of 7.4 volts and a maximum 8.2. Well, I fed it with a handful, 2 or 3 different types of resistors, and it comes in anywhere between 7.7 and 7.9 volts. So going back to the SAK circuitry, you've got those 2 resistors on the high side. In this particular circuit, they moved that high side resistor going in as your main supply voltage. They moved it to the low side. So the the sample circuitry is 100 ohms, but I've measured that this low side resistor, this printed resistor, is about 200 ohms. I say about because it's broken, and it's probably why the thing stopped working in the first place. Or at least one of the reasons. You can actually see there's some cracks in the capacitors and the rest of it. They still measure okay, but that's not a good sign. So you've got your negative coming in here, it goes down along and into this printed resistor, and then off into the grounds of these and into the pin 1 over here. Now, the way that I actually figured out what that resistor was is I just basically put one lead on there and just started piecing the resist on there, and it kept measuring until I found it, and then I noticed a discoloration in the resist there. And it coincided basically with where I was able to get measurement from this side to that side and from there to this side. So, long story short, is roughly about 200 ohms. Now, and it's quite big, and that's important because if you do your maths on a voltage car power supply, they're like running anywhere between 14.2 and probably worst case 15 volts. At least you have to allow for that. And at those sorts of dissipations with like 7.7 volts across this device, and that then going to be best part of a quarter of a watt, if not more. I mean, some of those, if it goes more than 15 volts, it's going to be more than a quarter of a watt, which probably explains why that it damaged itself, why it broke where it was. But I managed to find a 200 ohm quarter watt resistor. Yes, 200 ohms. That's an unusual one. I did measure, so it's red, black, brown, instead of red, brown. So yeah, it's just I pulled it out of an old TV circuitry board. When I first saw it, I thought it was 1 key, and then realised no, the third one's a tens multiplier, and I thought, hey, what? No, measured it. Yeah, it's 200 ohms. So I'm going to whack that in between the grounds here and that point there to re-enable that circuitry. I'm going to have to put that capacitor back on, which was spot welded between pins 7 and 1. I'll have to reattach that. Obviously can't spot weld it. And then run some tests. Now there's a printed circuit board switching mechanism here, which is gone. The knob has disappeared, and the wafer is around here somewhere. At any rate, I'm not going to worry about where that is, because it's going to be impossible to figure out what's what from that. Like, you know, which position is for 4, 6 and 8 cylinders, I'm assuming. Yeah, so you can see detents for at least 3. There's another 2 on the end. I'm not sure whether they're just stoppers or not, but there's at least 3 positions in this switch. But where that wafer is in relation to the switch position and which position is what, it's a good question. So, having said that, the circuitry already has at least one type in circuit, so it should work. And I'll just feed it with my frequency meter and then do some measurements. So let's I'll get that all back together again and do some testing. So I've just hooked up the meter, so we can. So I've got that. I've got current meter measuring on the METEX, and I've got the voltage across the RPM meter on the 10 bar. So I just got a limiting resistor in here, so that when I adjust the voltage, I've got some room, and we can see that it's at full scale at 8,000 RPM. According to that, we're drawing 10.33 milliamps with a terminal voltage on the meter of 1.7 volts. So half scale's what, 4,000. pretty linear. So yes, it's a bit wibbly wobbly. Pegs. And doesn't take kind to being disconnected. Listen to it. So there's the movement. These counterweights. As you can see, the power comes in and actually tracks in along the wire. The springs themselves are actually conductors to the meter movement, same as the positive side. Okay, so I've attached the that 200 ohm resistor in there, and I've just glued this stuff in with a bit of fast grip. It's that contact adhesive basically, but there's a bit of a design issue here, so I don't want to use that when high voltages are concerned. And even though there's a 47k coming in from the trigger, it's right next to the earth. You can see that point there, and specifically that capacitor there is very, very close to there. So to provide some electrical isolation there, I'm just going to use my old faithful, my ester pole. And just gonna drip it in there to provide me some electrical isolation and some mechanical strength as well once it dries. So I still need to attach the electrolytic capacitor, so I just need to clean those the leads off 1 and 7 and solder it on. So I'll just leave that to dry for a bit. In fact, I'll tilt the board, let gravity work its thing. Okay, managed to get that capacitor back on, and just a final check. .35 microfarads. Okay, so I've got the circuitry all fixed. I've separated, that needs to mount on the back of that, but I've just left it separated so I can do some measurements and stuff like that. So I've got 12 volts coming in, I've got my frequency generator, my function generator coming in onto a little board here, and pretty much nothing on that board is being used other than that MOSFET there and support circuitry around. That's all I'm doing, is I'm just amplifying my function generator's output, which is about, I don't know, about 1.9 volts or something peak to peak, and I'm upping it up to, that's a good question, and it's outputting 10 volts peak to peak at a frequency of 39, basically 40 hertz, and it's showing 1000 RPM on the meter. So that's okay. That's closest to a 4-cylinder. A 4-cylinder at 1000 RPM theoretically is 33 in the third hertz, 33 in the third cycles per second. And the way that I derive that is we're talking about a 4-stroke engine. So there should be 2 sparks per revolution and 1000 revolutions per minute. You divide that by 60, you get 16 hertz, and so you double it for the 2 sparks per revolution, and you get 33. And likewise, you can make the calculation. So for a 6-cylinder, that would be 50 hertz, 50 sparks per second, and an 8-cylinder is double a 4-cylinder one, so 66 2/3 cycles per second, hertz. Okay, so I've got my power coming in there. I just got just under 12 volts coming in here. It's split. That's normally connected to this terminal over here, and obviously in order to be able to separate it I need to add this extra bit of wire in, and I've got 11.96, let's call it. Okay, so that's coming in here, and it's across the capacitor. Now remember, I've got a 200 ohm on the low side, and that's effectively a Zener across there. So if I measure from this, I don't know, what would you call meter ground, and we measure so we've got 7.8 volts. So now, and the meter's outputting. So let's take a look at it using the crow. So on the oscilloscope, I've got my got the signal as it's coming out of my little circuitry, an amplified signal. So that's on channel 1. That is in turn being fed to the component side of the tacho. So I'm skipping over the 47 k ohm resistor there. That's going into the tacho entry. That makes its way to pin 2 and then into this circuitry. So if we take a look at what's on the meter, it's not going to be pretty from what I recall. Yeah, it's quite a bit of noise. So it's sitting at the high end. Now remember, the meter is, this is going to go lower as the RPMs go up. And so all of that extra, those spikes that we see, the under and overshoots there, they would be due to the inductance of the meter movement itself. So reading the circuit diagram, it tells you that the current that's coming out of pin 5 is actually a mirror of that coming from pin 6. So if I get my eyes on and angle this right, there's pin 6. And if I now, don't move. Okay. If I turn the frequency up, you can see the way it behaves. And you can hear it. That noise is actually coming out of the meter. And so the circuitry is over here. So that the signal I'm going to look at is on this 63 nanofarad capacitor there. This side of this capacitor is actually coming out of pin 3. Okay. Let's turn the frequency down so I can. Let's take it back to 1,000. That's about 1,000. So that's an interesting waveform. And pin 4, here we go, there's our charging current, and by the looks of that, it's a constant current. Well, it's a little bit of a curve on it. Best part of a constant current. So that's 304 hertz before you start running out of pulse width. But then the meter still moves up beyond that. So you can see we basically start to see the charging of the second part of the waveform. Some people will call that fold back or whatever, but basically we just run the period that we're using. It's very similar to the output of the 2907. I'll do a separate video on that, just to do as a course. I'll do this one now just to show you how it looks. Essentially what we're seeing here is I've heard it variously described as pulse width modulation. Let's go to pin 6. Right? But I think that's too misleading. What it is it's a fixed pulse. See the positive pulse there. But what happens is they collapse the period over which those pulses, so the pulses come together. So yes, it's in depending on your point of view, you could call it pulse width modulation, but the width that you're modulating is the off pulse, right? How would I describe that? I would call that a fixed pulse variable period, or period modulation, or something to that effect. And that's a common theme throughout these frequency to voltage type conversion circuits. Oh, just as a point, this what you're seeing here is at the beginning part of it. That's just a bug in the oscilloscope, so don't worry about the bit leading part of it. Getting the back part of this meter on is a bit of a pain in the butt. Once you get the magnetic shield on. Make sure you bring the wires around the right way, and this goes in at an angle to the meter movement. And there's a little locating stud there, plastic stud there, it goes into that little hole there. And then the screw holes should all just line up. And once you've done that, then it's a matter of soldering those wires on. Okay, so the red wires are going to. I need to make sure it goes over little brass bit so it doesn't interfere with the movement, and that goes onto there, and that black wire goes down to the meter down there, meter connection there. In terms of mounting it, there's that plate goes on, and then this screw with the non-threaded part, it goes on to hold that plate on, and then these three, there's supposed to be a third shake-proof washer, I don't know where that is, and they go in and hold in the back of the case. That's the cutout for the screw that needs to go in beforehand. Yeah, that cutout. Little bits there. Okay, so I need to get that onto there, and all of these connections were spot welded before, so I have to get rid of kinds of crap off here. Clean up where it was spot welded before so I can solder it. They spot weld them because it's obviously if you solder it, it can theoretically melt, but I think more importantly, the solder in a high vibration environment creates a brittle connection, so that's why these things are spot welded. The strands are free to move. It's not going back in a car, but you know, it doesn't hurt to do a half reasonable job, just in case you do want to go actually use it. To glue that into place. Okay, that's those connections all done. I'm going to leave these wafers out. Just to protect the dial. So it needs some calibration. Probably putting that 200 ohm resistor on the low side has had an effect on the calibration. So 40 hertz gave me 1000 RPM when it should have been 33 hertz. So, but that's basically how an RPM meter works, an old school one, an old analog RPM meter. Not a very good meter movement. There's no damping in the meter movement on this thing, as you know, evidenced by the springiness of it, and the operation of that circuitry with the pulse and the amount of movement that it has. It requires that springiness, because there's you send a pulse, and then the springiness is going to bring it back, and so it averages out. right? So you can imagine just this ping, 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 and it just keeps going around. And you heard it when it was up in the high. You could actually hear the movement singing, and when I grabbed hold of the needle, it quietened down. Yeah. And this is an electronic one, so this is working off the spark. And as I said before, on a 4-cylinder 4-stroke, there's 2 sparks per revolution. So a stroke is, that's stroke, 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 stroke. That's 4-stroke. So you can imagine the rotational shaft, that's 2 rotations for every 4 strokes. Let's finish on the meter face.